Welcome to this video on the fundamentals and derived quantities, covering our first week's introduction to physics measurement. Welcome to your physics course. Our journey begins by exploring physics as the study of matter and energy. We'll learn how measurement serves as the language of science to describe the universe using numbers and units. In this video, we have three learning objectives: defining physical quantities and their roles, classifying them into fundamental or derived categories, and applying the globally recognized SI system of units. A physical quantity is a property that can be quantified by measurement. It consists of two parts, a numerical value and a unit. For instance, in 5 meters, 5 is the value and meters is the unit. Why do we need units? They ensure accuracy for precise descriptions, enable standardization so scientists can share data globally, and provide essential meaning to numerical values. Physical quantities are classified into two groups: fundamental quantities, which are independent and form the foundation, and derived quantities, which are obtained by combining fundamental ones. Now let's look at part 1, fundamental quantities. Fundamental quantities, also called base quantities, do not depend on any other quantity for their measurement. There are exactly 7 of these in the SI system. This table lists the 7 SI base quantities: length, mass, time, temperature, electric current, amount of substance, and luminous intensity, along with their respective units and symbols. The first is length, defined as the distance between 2 points. Its SI unit is the meter, and common measuring tools include meter rules, tape measures, and vernier calipers. Next is mass, the amount of matter in a body. The SI unit is the kilogram. Common tools are electronic or beam balances. Notably, mass remains constant throughout the universe. Third is time, the interval between two events. The SI unit is the second. We use tools like stopwatches, clocks, and atomic clocks to measure it. Fourth is temperature, representing the degree of hotness or coldness. The SI unit is the Kelvin. Thermometers are used for measurement. And a fun fact: 0 Kelvin is absolute zero, where all motion stops. Fifth is electric current, defined as the rate of flow of electric charge. Its SI unit is the ampere, and it is measured using an ammeter. Finally, the 6th and 7th quantities are amount of substance, measured in moles for counting particles in chemistry, and luminous intensity, measured in candelas to indicate the brightness of a light source. Remember, every other unit in science is made from a combination of these 7 magical building blocks. Think of them as the letters of the scientific alphabet. This brings us to the SI system, or the International System of Units. Adopted in 1960, the SI system is used globally. It serves as a universal language, provides precision through unchanging physical constants, and offers easy scalability using decimal prefixes. Metric prefixes help us scale units easily, from the 1,000-fold magnitude of kilo down to the millionth part represented by micro. Now let's move to part 2 of our video, derived quantities. Derived quantities are those that are calculated from fundamental quantities using mathematical operations. For example, area is length times breadth, measured in square meters. Volume is length times breadth times height, measured in cubic meters. Another example is speed, which is distance divided by time. Its unit is meters per second. This table displays various common derived quantities, showing how they relate to the base units we discussed earlier. Some derived units have special names, like the Newton. Named after Sir Isaac Newton, this is the derived unit for force. Pressure is another example, defined as force acting per unit area. Its SI unit is the Pascal. To summarize, fundamental quantities are the base, while derived quantities are calculated from them. As science has progressed, our need for standard, consistent units has only increased. This timeline shows the evolution of measurement, from ancient units like feet and cubits to the standardization of the SI system in 1960 and the redefinition of the kilogram in 2019. In daily life, about 15% of our measurements involve fundamental quantities, while 85% involve derived quantities used for complex analysis. To wrap up our session, keep in mind these words from Lord Kelvin: "To measure is to know. If you cannot measure it, you cannot improve it." Let's test your knowledge with a quick review. Can you identify if volume is fundamental or derived? What is the SI unit for temperature? What tool measures electric current? And how many fundamental quantities are in the SI system? Remember these lab rules for accurate measurement. Watch out for parallax error by reading at eye level, check your tools for zero error, and always take multiple readings to calculate an average. To summarize, physical quantities are anything measurable. We use 7 base units as the building blocks for science and derive additional units for more complex calculations. That concludes our introduction. Do you have any questions about this week's content? Great job today, class! In our next lesson, we will continue our physics journey by exploring scalars and vectors. See you then. This video used various resources and images to illustrate concepts. Please refer to these sources if you would like to learn more. Additional imagery used in this video is sourced from the providers listed here.